Welcome to the March 9th, 2015 M-OSRP Executive Summary. As you can see on the upper left side of this slide, under M-OSRP it says solve the right problem. What solve the right problem means is identify, address, solve, and deliver solutions to problems that will have the biggest positive impact on our ability to locate and produce hydrocarbons. That's a tall order, but that is our commitment. And in this presentation today, we will show you evidence of that impact, documented evidence by a published public record of how industry has benefited from what we have delivered, what are the current projects within the program, what problems are they addressing, and why is M-OSRP uniquely positioned to deliver that necessary next level of capability. So that's basically what this executive summary is about. There are several associated videos that provide detail of what this is a succinct overview of. One is a February 20th video that you will see in a link near the link you just clicked to see this video. There's another video that's a keynote address to be presented in Abu Dhabi at an FWI Filling the Gaps SEG workshop at the end of this month. And last but not least, there is a link to a presentation for our sponsors on multiple signal noise. So those additional links provide detail and discussion and examples that complement and define and delineate the topics in this succinct summary. So why are there seismic exploration challenges? There are challenges because every seismic method that ever has been and is and ever will be has assumptions. And when those assumptions are satisfied, methods are effective. And when those assumptions are not satisfied, we have algorithmic failure, and that can contribute to dry hole drilling and suboptimal development drilling. If you need evidence that there is a dry hole drilling issue, please check the Department of the Interior Mineral Management Service statistics that show 1 in 10 exploration drilling in the Deepwater Gulf of Mexico is successful. 1 in 10. And that rate of success has not changed in 10 years. So there are challenges. How do you address challenges? There are different ways. If the method has assumptions, you can look for better ways, new, more effective ways to provide and satisfy those assumptions. Another way is, if you can't find a way to satisfy a method's assumptions, then develop a fundamentally new method that doesn't have those assumptions. A third and unfortunate way of dealing with terrible, difficult challenges is simply to ignore them. And that is not something that this group will ever subscribe to. The challenges we deal with are the toughest problems, and just saying that there are problems already can cause issues with people who choose to ignore them and act as though they don't exist. So if you want an example of such an issue, I would refer you to the outstanding presentation by John Etchen of BP at the last SEG in Denver in the Recent Advances Road Ahead, where he stated that the greatest challenge in exploration seismology today is due to the inability to have an adequate velocity model under complex subsurface conditions. That tomography, common image gather flat, FWI, innately don't possess the capability to fill the gap between the problem, the scale of the problem, and what they represent. That's a very serious and rare statement, And that's one of the kinds of issues that this group is fully cognizant of and looks to provide solutions to. Another example is the year before that, at a workshop on internal multiples, Bill Goodway and David McKidd from Apache and Encana gave a talk on internal multiples on land, the elephant in the room. They faced throughout their careers the simple avoidance, the refusal upon with their colleagues to recognize that multiples even exist, let alone are a problem that is difficult to deal with on shore. So those are examples of challenges. There are no shortage. Those are merely two examples. So this is a figure that describes the history that an event goes through from the moment it's collected in the upper green, and every event is collected in that upper dot, and then what happens is the events are separated into what we would call a reference wave and a reflection data, and then the reflection data is separated into events that have ghosts and reflection data that do not have ghosts. And then the reflection data that do not have ghosts are further separated into primaries and internal multiples, separated from free surface multiples. And then primaries and internal multiples are further separated into primaries and internal multiples. First approximately, then in principle exactly. Then the primaries are depth imaged, inverted, Q compensated without Q. This whole chart, every single bullet on that chart, every single link in that seismic processing chain has had a positive, significant impact from our history, and and that history has benefited M-OSRP. By that history, I mean my colleagues, former students from before I arrived at M-OSRP, and the enlightened management at ARCO, at Petrobras, at Schlumberger, that gave us a chance to do work on significant high-impact problems with methods that were often controversial, or often met with lots of skepticism, and now as an industry we benefit from. On that chart there are two kinds of colors, green and yellow. The green represent green steering methods that improve your ability to separate reference wave from reflection data, improved methods to do deghosting in both X omega and in K omega, methods to separate the primaries and internal multiples from free surface multiples. This yellow dot represents the inverse scattering series, and that dot represents what Carvalho and company provided, which is the most effective method that has been and is for eliminating free surface multiples without any subsurface information. That method is not SRME. SRME, this industry standard for free surface multiples, does not provide an accurate amplitude at every offset. And if you're interested in that kind of thing, we suggest you look at the code that Carvalho pioneered and this group delivers in 2D and 3D. Then you have a further separation of primaries and internal multiples into primaries and internal multiples by the inverse scattering series, and then primaries are processed to depth imaging without a velocity model, direct inversion for medium properties, Q compensation without Q. This item here, direct inversion for medium properties, I refer someone who's watching this video to our Abu Dhabi video, which goes along with this, which gives a framework for FWI that's based on solid physics, the fundamental relationship between change in wave fields and change in medium properties, and recognizes that the elastic equation for the simplest isotropic heterogeneous Earth has coupled P and S waves. And that gives an entirely different framework for how one should approach FWI in contrast to what people are doing in the industry today. Okay, there's one anomaly here. You see a green item where this is pointing green, meaning green steering. Green steering for us is a method, very old, 1828, George Green. It's a method for wave separation and also wave prediction. There's a new and more capable, fundamentally new and more capable method of RTM that's being pioneered, developed, and delivered from this group that has advantages, significant substantive advantages for amplitude analysis compared to all current RTM methods. We'll say a word about that later in this talk. And including for specular and non-specular imaging and for imaging beneath rapid variations in velocity. So the bottom line here is every single step in the seismic processing is M-OSRP's business. Anything that has to be done before is our business in order to get the prerequisites of these more ambitious procedures. These earlier steps in the chain. And these earlier steps in the chain have to be done effectively. Again, the green dots represent added value that this group has provided to satisfy what a method requires. These wave separation methods, the ghost and not ghost, is not just needed for all multiple removal methods that we deliver, but of course this has broadband applications, having a more effective method for deghosting, for example. And so the green dots are where what a method, current method, requires, and we're providing it in a more capable way. The yellow dots are where we're providing a new algorithm that does not require what current methods require, demand, and have as assumptions. So this is a table of contents, which we won't go through in detail, of this associated video that was taken on February 20th, where you can see every project in this group. The people who work on those projects spoke, and you have the topics and the time in that video that you can scroll to if you have a specific interest. So I started off with some kind of overview, as I'm repeating now. Then there was a new methods for Green's theorem, as you saw up on the top of that seismic processing tree. There was a bunch of green dots. The added value of those procedures compared to current deghosting was shown on scene data and field data by Jim Mann. Then there was a very impressive set of work done in a student, Andre Ferreira here, done in cooperation with Petrobras, at Petrobras, showing the impact of the Carvalho free surface elimination and the internal multiple attenuator on deepwater Brazil multiples. Then Chung Fu showed the first onshore application work he did while he was at Saudi Aramco. Then what we're very happy about that internal multiple attenuator. It's gotten a lot of positive attention, as you'll see, but it's an attenuator. And every method that you will ever have has assumptions. The great power and standalone capability of the internal multiple attenuator, as with every single bullet on that chart, the green dots and the yellow dots do not require subsurface information. The only exception is that new form of RTM, which is conventional and requires a velocity analysis. Except for that, there's nothing on that chart that requires subsurface information. They're all direct and data-driven. Both direct and data-driven have been abused some. What data-driven means, directly in terms of data, you get the output. There's no other information. You don't seek information. There's no subsurface information. Direct, you'll see in a minute in that Abu Dhabi talk, if you look what direct means. It means like solving a quadratic equation. It doesn't mean searching or iterative linear or no cost functions and so on. So there's not a single step in that whole chain that's indirect. Now that direct and data-driven have gotten some good press, everybody in the world is data-driven, even those who are finding velocity. And now we find direct methods of indirect inversion. So that's natural. It's what do they say? Imitation is the sincerest form of flattery. So there's certainly some of that going on. Direct, indirect method. Interesting. As long as they get the direct word in. Okay, so we have a presentation by Yang Li showing internal multiple elimination, Chow Ma showing a new algorithm that addresses one of the shortcomings of the internal multiple attenuator. The attenuator can take internal multiples as sub-events and cause spurious events, predict spurious events. What Chow did is looked in the series. The series anticipates that issue, gathered up terms that address that shortcoming of one term, and provides a new algorithm that has the benefits of the internal multiple attenuator without that shortcoming. Jinlong Yang showed the impact of deghosting in radiation pattern and showed how to incorporate radiation pattern within the ISS multiple algorithm. This program is not just looking at marine, fully committed to onshore processing in general. Jing Wu showed us how to get some of those green dots for the pre-processing, the elastic wave separation of the reflection data from the reference wave, and then we do deghosting for onshore data. There's a presentation based on the work of Lin Tang, with how do you estimate near-surface properties indirectly. We're looking at ways that methods for buried sources and receivers for 4D application that don't require any information above the buried sources and receivers, below the buried sources and receivers, or at the buried sources and receivers. We will report on that at this annual meeting in June. And Xinlu Lin here showed how important it is to incorporate a 3D source in your internal multiple algorithm. If you have a 1D Earth or a 2D Earth assumption, you can have those assumptions and they might be reasonable in some piece of the Earth, but the 3D source is essential to have your algorithm accommodate that. Then we have a set of presentations, which is inverse scattering, series tasks, isolated tasks, beyond multiple removal for imaging, Q compensation, and parameter estimation. Fang Lu and Eyal on new and very impressive results on Mamusi, which you'll see in a few minutes. And Haiyan Zhang pioneered how to do ISS direct inversion for 4D application. And we're going to look at inverse scattering series for velocity analysis. And then there's work of Lira and company on ISS Q compensation without knowing or needing Q. Amazing. Q compensation without needing or knowing Q. Amazing. All from one set of equations. The same equations that bring you pre-surface and internal multiples bring you Q compensation without Q, depth imaging without the velocity, and parameter estimation without needing to know anything above the target. This is a totally separate topic which came to us by accident, which is a new way, it's not a new way to do RTM. It's not a cosmetic, it's not a common angle, it's not some way to more efficiently or cosmetically change current thinking. It's going back to what Claerbout taught us, that among the three imaging conditions, the superior one in terms of physics and understanding what the image means is Claerbout imaging 3, which is predict what a source and receiver would record at depth when they're coincident at time equals 0. We have arranged within this group recently to have what that experiment requires in order to use surface data. How do you arrange for that experiment where waves in your medium are moving up and down? All current RTM methods are Claerbout imaging 2, which is the time and space coincident of up and down waves. Those are innately and intrinsically inferior in terms of amplitude analysis, and they struggle to get through a discontinuous boundary. Claerbout imaging 3 with the new methods we have developed in this group don't have any problem getting through it, a rapid variation. So that's what all the detail of these presentations you can find in the associated video called February 20th, M-OSRP, February 20th, 2015, M-OSRP Executive Summary. So among these many contributions, we're going to just point out two. One is that this group, benefiting from all of our collaborators before I arrived at U of H, and all the tremendous students and professors within the group since I arrived at U of H, all of that, those people have provided the most capable methods today available for free surface and internal multiple removal. They have one quality that separates them from all other methods. They do not require subsurface information. Directly, indirectly, they don't need any interpreter intervention about where the generators of the internal multiples, what gives rise to those multiples. No information, no selection. All internal multiples and from all generators at once are attenuated directly and without subsurface information. Only the inverse scattering series brought that capability. Going along with that are all the pre-processing methods that you saw in that seismic processing chain that are required to be performed effectively in order for these multiple attenuation methods to reach their potential and to deliver their promise. So we're going to show you a sampling. In other words, where's your evidence that what M-OSRP has pioneered, developed, and delivered has made an impact? Well, the evidence is one part of what the usage must be. We're just going to show you a sampling of the published work that refers to this method explicitly and that it came from this group. The list of service companies, CGG, PGS, and Schlumberger Western GECO, have published works, and we'll show you some quotes on the standalone capability of the inverse scattering series method for internal multiple. This is a list of oil companies that have published documents, public record of the value that the inverse scattering series methods delivered from this group, either directly to them as sponsors or through their use as clients of those service companies, the benefit they have provided. This is a long list. These are service and oil company references. So we're going through these slow enough in case you want to see and follow up and look at these references and see what they actually say. These are oil companies that have published SEG abstracts or papers that speak to the effectiveness, standalone capability of what M-OSRP has delivered. And it goes on for a while. They have Exxon, Shell, Aramco, ConocoPhillips, just on one chart. So here are a few quotes. There's a quote from a Petrobras slide. No other tested method was able to attenuate the sequence of internal multiples below the salt layers. If you want to see those results, please see the February 20th video. It shows all of these in great detail. Here's a quote from CGG. The 3D inverse scattering series method for internal multiple attenuation, data-driven approach that can predict all internal multiples without any a priori knowledge of subsurface information. It doesn't require any information a priori or a posteriori. It doesn't require or know anything about the Earth before, during, or after the process. But that's a very positive and much appreciated comment. Here's Aramco. Their internal multiple, ISS internal, was demonstrated with complex synthetic and challenging land field data sets with encouraging results, where other internal multiple suppression methods were unable to demonstrate similar effectiveness. These companies are not just sponsors of this consortium, by the way, as you can imagine. There's a Schlumberger publication with a similar positive quote. It's purely data-driven and does not assume a priori. The reason they're saying it is there is no other method that does, that satisfies that property. Our plan is to progress everything on that seismic processing tree, every bullet right to the very end, for offshore towed streamer, for ocean bottom cable, and for onshore, including 4D application with surface sources and receivers and buried sources and receivers. That whole tree, for all of that. We said that we're very happy and pleased and gratified and grateful for all that positive press for the internal multiple attenuator, but it is an attenuator. An attenuator means it gets the exact time and approximate amplitude of the internal multiple. It's a one term in an internal multiple elimination process that was pioneered by Araujo and Company, and we are, so what is done in practice, if you have an internal multiple and its prediction, when you want to subtract it, it's not exactly a fit. So what comes along in addition to the prediction is an adaptive subtraction, energy minimization, adaptive subtraction. That step says that when you have the multiple removed, it's lower energy than when the multiple is there. That reasonable assumption has been essential. Without that fix, multiple attenuation methods would not have been effective. Yet, as with every assumption that's reasonable today, tomorrow it's the biggest obstacle to progress. Today, when you have interfering primaries and multiples, as can happen offshore and frequently happens onshore, the whole criteria behind energy minimization adaptive subtraction fails. When you have an interfering primary and a multiple, when you remove that multiple, the energy can go up, not down. So the criteria fails. We're committed to addressing that type of problem. You can have problems, as Bertrand Duque and his colleagues from Total published in the North Sea, where you don't have a velocity analysis problem. It's as flat as a pancake, but you have such a horrific set of internal multiples that interfere with primaries that is an obstacle to EMP effectiveness in the North Sea. They published that, I believe, in 2012 or 2013 in EAEG abstract, a group from Total. So for that kind of problem where you have interfering primaries and multiples, the ISS attenuator is not going to be, plus adaptive is not going to work. It's just going to fail. You'll remove the primary with the multiple. We need more capability. We need internal multiple elimination. We need to remove the spurious events that I alluded to. And we need a new adaptive criteria. This group is committed to that delivery and is uniquely qualified to provide it. The internal multiple elimination without subsurface information can only come from the inverse scattering series. It's the only set of equations that we know that say the following. Every single processing objective that you have in mind can be achieved directly and without subsurface information. So if you have a certain capture, which is ISS attenuate, there are other terms which will take you to ISS eliminate. We will show you right now Yang Li Zhou's work on synthetic data for ISS eliminate for a 1D Earth. This is synthetic data that Yang Li ran when he worked within Clement Kostov's group at Schlumberger. This is an elastic model, 1D. Red represents primaries, or the arrows that are red are pointing to primaries. P primaries, in fact. The green are pointing to converted wave primaries, and blue are P wave internal multiples in this particular example. Here you see a panel from that larger section where the input data, the attenuation, the elimination prediction. Here is the primaries in the data, because it's synthetic. He can generate this. This is a converted wave primary. This is what happened after the attenuator, and this is what happened after the eliminator. This comes much closer to this primary than the attenuator does. Here's a bit of numerical noise that Yang Li is resolving. That's an example where you have a primary and internal multiple interfering, and the current best capability in industry today fails. You would assume this is a primary. That's a multiple. You have some colored arrows here pointing to the different events. The red is the primary. In other words, what's going on here is you have two P only internal multiples boxing in a converted wave primary. Again, you can look at the February 20th video to see the detail. So this is comes much closer to predicting the primary with elimination than the attenuator did. The red. So here's a totally separate subject. This is what we mentioned, a new method for RTM. This method just realizes what Claerbout taught us in his famous 3 imaging conditions. There's Claerbout, in what we call Claerbout imaging 1, exploding reflector, Claerbout 2, time and space coincident of up and down waves, and Claerbout 3, which is predict what a source and receiver experiment would do at depth, make them coincident, and ask for t equals 0. This is Claerbout imaging 3 for two-way waves. This is new. We've only published this recently, and this compares. So this integral over geophone brings the geophone down, and then the integral over shot brings the shot down in this Claerbout imaging 3. So the integral over shot is not to reduce some noise. It's to do something which the physics says you need. You need to do a Green's theorem prediction to get the receiver in the Earth, and then you have to do a Green's theorem prediction to get the source in the Earth. That's in contrast to a formula like this, which is all current RTM, which takes a time and space coincident of up and down waves and sums over sources to reduce noise, some kind of artifacts that come about when you do this for one shot record. They sum over sources. Please compare that with the equation that was on the previous page, where the sum over source has a very explicit function to bring the source into the earth. It's not to fix anything wrong with the integral over receivers. So this has tremendous potential. We are examining this. Professor Fang Lu and Chung Fu are examining this and looking at the advantages that being able to apply Claerbout imaging 3 in a volume where you have two-way waves is required for RTM and other applications. This is an example, just a cartoon of what, again, you can see in detail. Using this formula, not this formula, you can get from reflection data with primaries and internal multiples and a discontinuous medium, the reflection coefficient above, below the first reflector, and above and from below the second reflector. Only two-way propagation and Claerbout imaging 3, that combination is new and being developed from M-OSRP. Will provide that capability. Here's Professor Fang Lu's results on Mimosa. This is part of the inverse scattering series, depth imaging without the velocity. What we just finished talking about, Claerbout imaging 3 for RTM, that is not inverse scattering series. That's conventional, needs a velocity model. We felt that if we can provide something within conventional, that's not cosmetic, that's not some mild variation, but has some significant fundamental improvement over what's done today, it is our obligation to communicate that, and we are. This is part of the inverse scattering series. No velocity information, no depth, no density information. Direct depth imaging, just like ISS multiple removal. There's no searching, there's no velocity seeking, there's no iteration, there's no cost function. This is depth imaging without a velocity model. This slide is saying that this is your data. This is a 2D example. This is essentially a form of Stoll pre-stack water speed migration. That water speed migration enters an algorithm called higher order imaging series, closed form, which collects terms in the inverse scattering series, whose goal, whose objective, whose purpose is to do depth imaging without knowing or determining the subsurface, or needing the subsurface. This slide is here to show you that there are certain terms that have not been yet included in these algorithms. We're just at the tip of the iceberg of collecting inverse scattering series terms that whose purpose is to do depth imaging. But that already, that current collection already shows the tremendous promise and potential. Here's a Mimosa model, the latest of Professor Fang Lu's results. Complicated model. This it gives you the modeling procedure that he used. This is the experiment, many shot records, of course. This is a shot record at the center of the model. This is a water speed image. This is where water, this is the green, the blue, the red are where structure are. This is where the water speed image is. This image belongs here, and so on. This is where the image is with water speed. This is where the structure is. So this is a single Fourier transform water speed migration. That is then put into Professor Fang Lu's inverse scattering series depth imaging algorithm, closed form, and produces this. The image and these, now those images on the left line up with where his depth image results. here. This was way up, now it's located. So again, this is a very complicated model. The capture of the inverse scattering series terms that are represented in this algorithm called higher order inverse scattering is the tip of the iceberg of capability, but this demonstrates the promise and potential that inverse scattering provides for doing depth imaging without needing a velocity model directly. Amazing, besides the fact that these results are very impressive, is the fact that the speed to go from the water speed image to this image takes 30% longer in time than a single water speed migration. So these are different angles. These three lines are showing you how you know here whether you have an adequate image. These are showing common image gather flatness. You see in the water speed at that line A, this is not flat. These are flat. This is not using common image gather flatness as methods used today as an indirect procedure to try to find the velocity. When this is common image gather is flat, it is a signal that this direct inversion method that does not need the velocity has achieved its goal. It's not an indirect necessary but not sufficient condition. When common image gather is flat in ISS direct depth imaging, it is a necessary and sufficient condition that you are at the right depth. It's not one among possibilities. So this, as it says, this is a small fraction of ISS imaging terms. Laterally exclusive terms will be studied and included. M-OSRP has a unique set of experiences and background to pursue this, as well as a unique set of background and experience to provide internal multiple elimination. So M-OSRP commits to identify, address, and deliver solutions to the most significant and highest priority problems. That's what solve the right problem means. We have shown you today in this video the documented evidence industry-wide that methods which only have come from M-OSRP and that were controversial, raised lots of skepticism 20 years ago when you said that you can do internal multiple attenuation or elimination without subsurface information uniformly from every consortia other than where we were working, from every academic enterprise, from every oil company, service company. We heard nothing but that's impossible. Not only is it possible, today it is conventional and standard, and it represents in your toolbox of multiple attenuation procedures the most capable for one reason: it has no need for subsurface information. So in the history of multiple removal, methods started with stacking as a form of multiple removal, and then FK filters, and then radon, and then high resolution radon. At every step in that history and that evolution, there was more capability. You were able to remove a multiple with high resolution radon that had a smaller move out than a stacking difference, more capable, but it had a greater demand on an accurate velocity. The evolution, all of a sudden, ISS comes along and says free surface and internal multiple doesn't need anything about move out differences, doesn't need any subsurface information, no velocity, and is more effective than all of the methods that came before it for free surface and internal multiples. If you look at the evolution of processing primaries, start off with post-stack time, post-stack depth, pre-stack time, pre-stack depth, RTM, migrating with anisotropic velocity, and every form and twist and turn of RTM. Every single step in that evolution has the capability of more able to accommodate more complicated velocity model if you could find the velocity. We're saying, just as there was an alternative in the history of multiples, that alternative sits there for processing primaries. And we're looking at it. We know that that brings a lot of skepticism. We're not committed to being popular. We're not committed to running for an election. We're committing to two things: solving real-world problems that are most significant and serious, and producing the high-quality students who produce these results. 7 of our students in our history have been awarded the Karcher Award from the SEG, and that's a tremendous testimony to their capability and dedication and contribution. Again, I thank you for your support and your encouragement.